Hello everyone, Professor Dustin here, and this video is going to be a solution video to the Projectile Pint whiteboard. So on this whiteboard, we have this bottle being slid down a bar, and it's going to fly off of the bar and maybe land on this person standing a distance d away from the bar. So this is a combination of certainly kinematics, because we have a kinematic motion in one direction here. We have a 2D kinematic motion, which is when the bottle falls off. And then of course we might have to deal with some Newton's laws, because to figure out what the velocity of the bottle is, we have to know what the forces on the bottle are. So there's a variety of things going into this problem. Set up the problem is that the bartender is sliding the bottle from the end. Initially, we have the force of friction between the bar and the bottle is 0.15 newtons. So be a little careful with how we interpret that information. It's the force of friction. It sounds like it's kinetic friction because the bottle is moving, but we're not going to have to actually use mu k, the coefficient of friction, because we're just being given the entire friction already. And the bottle has a mass of 0.52 kilograms, so I'm going to call that m. And the question is first asking what is the acceleration of the bottle as it travels down the bar. So we're given a collection of information which includes the force and the mass, and we're being asked for what the acceleration is. So that's a question based in Newton's laws, right? Given the forces, what is the acceleration? So the first part of this problem is going to be using Newton's laws to find the acceleration of the bottle as it travels down the bar. So I'm going to start with a free body diagram. Should be pretty straightforward here. We have a bottle which has some mass, so that has some gravitational force. It's sitting on the counter, sliding on the counter, so it's got a normal force. There is a frictional force. The bottle is definitely moving to the right, so the frictional force wants to oppose that motion. The frictional force will be backwards, right there. And then we have to think if there's any forwards forces, any forces making this thing move in the positive x direction. The answer is no. After the bartender lets go of the bottle, no additional forces are acting on the bottle. And remember that we always, unless explicitly told to do so, we always sort of assume that however the thing started in motion is not our concern. Mostly that's because it would be very difficult to figure out what the bartender is actually doing as he slides the bottle. So it's kind of like the throwing motion, right? When we throw objects in physics, we don't worry about how the object is being thrown. We only worry about it has been thrown and then is moving. So that's a similar case here. So my point is that we have only three forces acting on this object, and to find the acceleration, we need to use Newton's second law, which means we have to sum up the forces in the x and y directions. So let's start with the x direction, because that is pretty easy. That is simply minus Fk, because the only force is in the negative x direction. I guess let me be very clear and stick a coordinate system on this thing, so that the bottle is moving in the positive x direction, so the force of friction is in the negative x direction. That's equal to mass times acceleration in the x direction, just to be clear. In the y direction, we have a normal force, we have a gravitational force, and we have no acceleration in the y direction, at least before the bottle goes off the side of the bar. After the bottle leaves the bar, it's going to have some acceleration, because it's going to be in free fall, right? But at the moment, those are the two Newton's laws, and if we're asking for what the acceleration of the bottle is, clearly what we're going to do is simply solve Newton's second law in the x direction. In fact, we have almost nothing to do because it's basically set up for us already. We know what Fk is, we know what m is, so we can easily find the acceleration. So I can just divide by m and get that the acceleration is minus Fk over the mass. And that gives me an acceleration of minus 0.29 meters per second squared. You can see that it's negative. That makes sense because the bottle is slowing down. After the bartender slides it across the bar, there is a frictional force in the negative x direction slowing the bottle down, and so we would expect to see an acceleration which is negative, which we indeed do. Okay, great. Let's go on to the next problem, next part. Okay, so in part B, we know that we're given that the bottle started at a speed of 2.97 meters per second. What is the speed of the bottle as it leaves the bar 2.8 meters away? So the bottle is now traveling down the bar, and we want to know the speed right there. And so I think I'm going to call that VB, because it's the velocity in part B. So I could say VF, but the next part is also going to have a velocity in it, maybe, so I'm just going to be clear and say VB to be like during part B. That's the velocity after it flies off the bar. It's 2.8 meters away, so I'm going to label that a distance d. And we already have a label for V0, which is 2.9. 7. So to do this, now we know what the acceleration is. So we have an initial speed, we have an acceleration, we have a distance. Clearly this is going to be some kind of kinematics problem where we don't have to worry about the forces anymore because we now know what the acceleration is, and so we can just worry about the motion. Sort of how the object is moving, not why the object is moving. So remember our kinematic equations, the basic problem we always have to answer is which kinematic equation do we actually want to use? Well, it's pretty obvious that at some point, since we need to find the final speed, there's only one kinematic equation that actually has the final speed in it, and that's the velocity equation. Vx of t is ax times t plus v naught x. So clearly that's the equation that we want, and in fact, we know some stuff already. We know what the acceleration is because we found it in the previous part, and we know what v naught is because that's the v naught given to us. The problem is that we actually don't know what the time is. We don't know how long it takes for this object to slide across the bar. So we're going to have to use our other kinematic equation to find the time. So that other kinematic equation is x of t is 1/2 a xt squared plus v naught xt plus x naught. So recopying that equation with the variables we actually have in our problem, I'm going to be clear that I'm keeping the same coordinate system, which means that I'm keeping the coordinate system down on this side. So where the bottle actually started is going to be the origin of the coordinate system, and so that means that the distance it traveled, which is x of t, is going to be d. It has an acceleration that is going to be that negative value from up there. Remember, what I'm doing is I calculated a negative value, so I'm going to leave the negative sign inside that ax, so that my ax is going to be negative. I might end up with some strange equations, but I just have to remember that when I go back later and put in a negative acceleration, those negative signs will cancel each other. It has some initial speed, v naught times t, and its initial position is going to be 0. So this is one of those times where we have to stop and look carefully at the thing that we've just written down. This is a quadratic equation. We are not going to be able to solve this just using algebra. No matter what we do, we will never be able to isolate the t's by themselves because we have a t squared and a t and a linear term. We have all three pieces, so we're going to have to use a quadratic equation. I just went to Wolfram or something and figured out the two solutions to this quadratic equation are 0.990 seconds and 19.6 seconds. So this is a situation where we have two positive values for the time. So we have to decide which of these two positive values makes the most sense. Now, if you think of the physical situation, we can sort of already come up with an argument for why the first 1.990 seconds makes the most amount of sense. You're sliding a bottle down a bar, right? It's going to take about a few seconds to get to the end of the bar. The 19.6 seconds, that's quite a long time. So it seems unlikely, given that the thing is slowing down, that the 19.6 seconds makes sense. But of course, we also want to try to figure out what that 19.6 seconds represents. So it's a physical situation that has the exact same numerical values that we have, that acceleration, that distance traveled, that initial speed, but it takes that long to do it. So it's a positive number, so it's going to be in the future. So to figure out what this is, let's start thinking about what happens after. Let's assume that this is true. Let's think about what happens after that. Well, of course, the bar is finite in length, so what's really going to happen is it's going to fall off the bar. But that's a different problem, right? These kinematics don't know anything about the falling off the bar thing. They think the bar is infinitely long. What happens if the bar was infinitely long and we had this acceleration the whole time? After 1 second, the bottle would pass this point, and then it would continue along our infinite bar, decelerating the whole time, getting slower the whole time. And eventually it would come to a stop as the acceleration gradually made it come to a stop. But of course, the problem is still giving it this acceleration. That obviously, like in a real case, static friction would take over and kinetic friction would go away, but that's not what this problem knows about. It only knows about the acceleration being negative. So it's going to keep going, it's going to slow down to a stop, and then it's going to slowly speed up and go backwards and then return to that same point at some later time, and that time is 19.6 seconds. So that's a pretty crazy idea, but I just wanted to point that out because, using kinematics like this, it implies you have to be careful the range of applicability of a particular solution. It seems very reasonable to be like, I take that acceleration, put it in here, we get about 20 seconds, that's just turning it around. Well, that's not what would really happen even if the bar was infinite, because once the object stopped, static friction would take over, and this would no longer be the acceleration. So applying these equations blindly can be a little dangerous because you might be getting into other actual physical situations. Okay, anyway, so we have the time. It is 0.990 seconds. So we can now plug it into the velocity formula, which looks something like that. And if you plug that into your calculator, you get 2.69 meters per second. So to do part C, I think I'm going to have to get to another whiteboard page. So I'm going to erase all this, but we're going to copy some numbers over that I'm going to use later. So Parsi is Black Hat from the webcomic XKCD. So you probably don't know XKCD, but it's a webcomic that deals a lot with like computer science and physics and math stuff, which I'm really a big fan of. The Black Hat guy, the guy with the black hat, is like a nefarious character who like gets into trouble in this webcomic XKCD. So I thought that he'd be the last person that you'd want to throw a bottle on, right? Just entertaining myself. So anyway, so he's standing nearby, a distance of 1.25 from the end of the bar. So that's telling us how far from the end of the bar he is, and that the bar is 1.15 meters tall. Let's put some values on that. Let's call this D, and let's call that H because it's a height. And we want to know, does the bottle hit him after it slides off the end of the bar? So let me try to get another picture of this. So now we've got the bar, the bottle being launched exactly horizontally because it's sliding off the top. And then it makes this projectile motion. It lands some distance away, and he is a distance d away. And I'm going to write x of t as a question mark because that's the distance we're going to find. We're actually going to find that it goes a distance x of t, right? What the final distance is. If it goes from a height h, of course this is the height h. We know what the initial velocity is. It's the velocity from part B. And we basically want to know, the easiest way to sort of formulate the question is xt bigger or smaller than d? You can do things like plug d into here and then figure out like what the time would be in order for it to fall and stuff like that, but that seems a little complicated to me. It seems better to just do something I know, which is calculating the distance from the end and then see if it's bigger or less than the distance that the person is standing away from the end of the bar. So first we have to acknowledge that our physical situation is now different. We have a different free body diagram. We're in projectile motion, so there's only one force going downwards. And so our kinematics are such that in the x direction there is no acceleration, and in the x direction the kinematic equations are relatively simple. That's good because at first glance what I need is the kinematic equation for x, because that's the thing that I'm looking for. So I'm going to write that down first, and then sort of inspect it to see if we have everything that we need. We have the initial velocity in the x direction. That's the initial velocity from part B. We know the initial position. We can just pick the initial position to be 0. That's sticking a coordinate system right here. I haven't picked that the bottom is 0 for h yet, but I'm going to do that. So let's stick the coordinate system right there. But we actually don't know what the time is. So this is a situation where the kinematics would be simple if we knew how long it took for the ball to fall. Remember, the previous parts have to do with the sliding across the bar, so we don't know what the time is for the projectile motion part, although we know what the time was for the sliding across the bar part. So this is another situation where we need to find the time. Finding the time is basically always using the vertical component of the kinematics in the y direction. That is, let me write that down. You're nearly always going to want to find, particularly if you're falling a distance h, you know how far you're falling, you're always going to want to use the vertical kinematic equation. And notice I've put the minus g as the acceleration in the y direction already, so I'm sort of using the projectile motion kinematic equations instead of the more general ones. But I can rewrite this equation, putting in all the stuff that I know just to make sure that it's what I want to use. My final height, I'm going to take that to be 0 because that's after it lands. I get the minus 1/2 gt squared part. There's no initial velocity in the y direction because it's moving exactly horizontally. And then the initial height is h. So it's just a matter of solving this equation, which can be done pretty easily. And you've seen this exact expression a few times, 2h over g. Move h to the other side, times 2, divide by g, take a square root. Anyway, the time that you get out of that is 0.484. seconds. And now I just need to plug that thing into this equation. And actually, it's a little bit safer to leave this as a variable expression, because then you won't be doing any rounding and your answer will be more precise. So I want to label this as like TC, like the time in part C. And so what I actually want to find is XTC. So that's actually there too. Anyway, so I'm going to put in VB, which is the velocity from the first part, TC, and the initial position is going to be 0. And leaving this at symbols would look like VB times 2h over g. That would be sort of the wisest to make sure that you don't have any rounding issues, but the answer you get is 1.3 meters. So indeed, that is further than the distance the person is standing, so it does indeed hit him, and the black hat guy from XKCD gets very angry when his shoes get covered in beer. Okay, so that's been the problem projectile pint. It's a good combination of actually 3 different ideas. First, Newton's laws, then kinematics in 1 dimension, and then projectile motion in 2 dimensions. So there's a lot of stuff in here, so it's a good practice problem for the exam that we're doing that's going to maybe include all those various kinds of problems. Okay, great. So I hope that has been helpful and clear. Thanks very much for watching, and I'll see you next time.